you can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car.
What's going on? Today we'll be talking about
object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. Here's another video from a more nominal sort of situation.
Like when there's occlusion, you're the red car, and you're blocked by this car having artifacts like this car, or there's like no line of sight here, so it assumes there may be a car. Thinks there's a car here, and then thinks there's like another car. So this is kind of like slightly different perspective from each camera, so then that's why it's making like duplicates.
With different perspectives on different cameras, couldn't figure out it's the same car, then it thinks that there's like two cars.
And basically the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. So very quickly we discovered that there's a large number of predictions we want to make that actually require the video context. We tried to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. And what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. So here's the feature queue and the rough layout of it.
So this is the queue for kinematics. This is the queue for the multicam features, and then this is the queue for the positional encodings. What is positional encodings?
It's like GPS.
Okay.
GPS gives you your position.
So your speed sensors is the kinematics, and then your cam features is the features I extracted earlier.
So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous feature.
So it's using the queue as as a memory, because they can look back and see there was some car in this area before.
That's right.
But the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. Because of the structure of the problem, we're driving on two-dimensional surfaces. We can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility.
It also reminds me kind of like the fog of war in like strategy games.
Here, what I'm going to show you is the car driving around, and these are different channels in the hidden state. Here's a few predictions.
It's pretty much doing mapping.
Right, it looks kind of like almost like a DFS.
Here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. The video networks also improved our object detection quite a bit. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone.
Single frame is orange, blue is video, green is radar. This is where they were doing their radar removal.
How the green line is so smooth, right? You can see it like in both examples.
Right, radar is definitely a lot smoother, but the multi-frame comes very close to that.
The video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. We have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module like the Spatial RNN. and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture, roughly what it looks like today. And on the right, you are seeing some of its predictions, sort of visualized both in a top-down vector space and also in images.
I am impressed by their depth. Like the depth that they were showing here, it looks quite accurate. It looks very stable, even from all these different perspectives. Like it looks very consistent. So I am definitely impressed by that. Definitely among like state-of-the-arts.
And as we have seen in our FSD Beta 10 review videos, now even with all this complex architectures and this feature space mapping,
right,
it still makes a lot of mistakes in many different strange situations. I feel like there are parts where showed us like how they did it, and they provided the paper on how to do that, and that's something that I definitely want to make future videos on. All right, well, that's it for this video.
All right, see you, YouTube.